Okay, welcome to Tables and Vectors. This is the maiden voyage of this presentation, so if it all goes horribly wrong, that's why. First things first, this is a link to the presentation. It's also posted on the agenda or on the breakout sessions page, so everybody will have all these slides, and there's no need to, for example, whip out your cell phone and start taking photos of the slides. Before I get started, I had a bunch of questions about, is this hands-on? And the short answer is no. This is a lecture-style session, but and so I'll have code snippets on the slides, and these code snippets may or may not work standalone, but on the bottom of each slide is a link to code that should work. And so you'll have the complete examples that we're talking about. You can open them up on your own time and play with the code and experiment, and so you'll have everything that we're going to work on today. And if something doesn't work, please do let me know so I can fix it. Okay, so Rebecca stole a lot of my thunder yesterday, unfortunately, or fortunately for her, I guess. But this is the new feature to announce, is that we have this native support for vector data sets. So previously, as you know, we had fusion tables, and that was fine. But now we have our own tables, and our own tables have some optimizations that let us do things like ingest really giant data sets of points. And some of those data sets we are hosting in the catalog. So if you go to the docs, which is available from the help button or developers.google.com/earth-engine, and you go to the reference tab, you'll see selected vector data sets. And so we've got a bunch of stuff here, including country boundaries, tiger data, so roads and census blocks, and roads, census blocks, glacier, a database called GLIMS, watershed boundaries, and EPA ecoregions. And this is just sort of getting started. We hope to have a lot more big vector databases hosted on Earth Engine soon. And if you have suggestions for large vector databases, please let us know. You can search for our vector databases the same way you would search for images. So type the keyword or the table name into the search tool at the top of the code editor, and you should see a new section called Tables, and you'll note that the Fusion Tables search is gone from this search tool. Instead, you will find a Tables section, which includes all the large vector databases that we're now hosting in Earth Engine. And if you click on one of the table names, you should get a little dataset description card like you see for images that describes the data and so forth. You can then click the import button, and it will make a variable referencing that data set in the import section of your script. So that's sort of the new, the shiny new tables part of Earth Engine that we're very excited about. And here's some examples. Roads. These are census roads, about 20 million road segments. And this is for the United States, but hopefully we can get more roads in the future. And this stores attribute data like the road type. Is this a surface road or a freeway or a county road or so on. That's a lot of roads. This is a data set from the Global Volunteer Observing Ships data, which one of our engineers has been working very hard to ingest. And I believe Rebecca showed this slide yesterday. The color here is the sea surface temperature measured by these ships, but there's a bunch of other information in there as well. This is just a preview. We hope to have this in the public data catalog in the very near future. So these are large databases that we've ingested for you and put into the public data catalog, but you can also upload your own vector databases by uploading a shapefile. And this should increase the limits pretty substantially over Fusion tables in terms of the number of points that you can get in there. Esri claims you can get about 70 million points into a shapefile. And there are some limitations on this that we'll talk about in a second, but we did a test run the other night in ingesting about 10 million GBIF points for South America from a shapefile, and it went off without a hitch. So that's good news if you have large shapefiles or large vector databases that you can turn into shapefiles. Those can go straight into Earth Engine by uploading a table. And like image assets, these are stored in your personal user folder, and they are private to you unless you want to share them. And we hope that you will share them with your friends and colleagues or with the world.
Nick, you say points, you mean any vector feature, right?
Yeah, 70 million points. So that's sort of like the simplest feature type. If you have more complex polygons, it's going to be somewhat less than that. Yes?
Are you saying the limit is basically by the file format?
The limit, yes, that's correct.
So there's no theoretical limit to the table size in Earth Engine?
Let me put it this way. The shapefile limits are 2 gigabytes file size on the .shp file. And Earth Engine's limits, as of now, are that it's got to be less than 10 gigabytes. I think that's should be enough for now, but if you run into trouble, let us know. And again, if you have a large database that you think might be useful to the Earth Engine community at large, let us know and we can try to ingest that for you. Other questions? Yes?
For the Tiger data, specifically the roads, is there any processing that y'all have done on it? Like, made road segments segmented by actual intersections or things like that? Because the Tiger's data itself is a little bit raw. Let's just say that there's like repeated lines, and one road might go along for kilometers, and another section is just a meter. So it's the road segments don't have as much meaning to the actual roads that say you might see in Google Maps or something like that.
Yeah, I probably have only a partial. Sorry. The question is, do we change the vectors when we ingest them or when you upload them? And the short answer is yes. They do get broken up for spatial indexing, and that's all I know. So if you have specific concerns specifically about Tiger data or census data, send me an email, and I'll put you in touch with our vector guy who can give you a much more detailed answer than that. Yes?
The shapefile format kind of limits this right now, but is there any particular reason, or is there a limitation on feature types within a table? Can you have, do they all have to be polygon or all points? Or can you have mixed geometry types?
I don't know the answer to that. Does anybody know, can you have mixed feature types in a shapefile? I think that,
The Shapefile, no, but I'm wondering if the storage engine and Earth engine is going to support multiple feature types.
I believe you can have multiple feature types. You certainly can in a feature collection.
Okay.
And as we're going to talk about in a second, these are just different back-end data structures that are essentially represented as a feature collection in the API.
And yes.
Yes, you can have different feature types.
The thing about modular is, to the best of my understanding, it's purely a matter of how shapefiles work, and we're going to let you have whatever in collection metadata files.
Okay, but right now we can only put a shapefile into a table, not multiple shapefiles into a table.
You could merge the tables after the fact. So once they become feature collections.
We can't save it, right?
I'm going to get into that a little bit more as I go on. I'm going to give you a sneak peek at some upcoming features that I think might start to answer that question. Yes.
You see that you also upload a projection file, so it supports any projection. It doesn't re-project on the fly. So
the question is, what about the .prj file? And the answer is it's optional. But if you don't include it, we assume WGS84. Okay, so a big part of this is this improved workflow. So once upon a time, if you had a shapefile, you had to either go through a website like ShapeEscape, which goes to Fusion Table, which then goes to Earth Engine, or you could turn it into a KML and then upload that to a Fusion Table and so forth. If you have tabular data, you could go straight to a Fusion Table, for example, as a CSV. But the big fancy new thing that we have is that this whole thing is short-circuited, and you can go directly from your shapefile into Earth Engine. And we hope to support more table formats in the future, but for now, shapefiles. Okay. As I mentioned a second ago, there are different data structures for tables on the back end, but these are all represented as feature collections in the API. So there are advantages and disadvantages to Fusion tables and or shapefiles. For example, a Fusion table has to fit entirely into memory. So if you have a smallish data set, a Fusion table is still a pretty good, fast option for you, if that's convenient. There are some limitations on file size, for example, 250 megabytes, megabyte per row, probably less than 100 properties, and importantly, 1 million characters per cell, which matters when you're trying to ingest very complex geometries as a KML file. You can quickly run out of space for those geometries. So those are some of the limitations of Fusion tables, but again, if you have a smallish data set, this is still a fine option for you. Earth Engine table assets, on the other hand, are stored as this column-oriented data store with a very good spatial index. So spatial queries or joins, for example, are fast on these tables. Non-spatial queries may not be so fast. So if you're doing some kind of heavy-duty attribute selection, or I'm going to use attribute and feature and property interchangeably, apologies for that, but that's sort of the GIS terminology creeping in here. If you're doing heavy-duty property selection or attribute selection, there might be a slowdown. You're limited by the shapefile spec, so less than 2 gigs per .shp. This is actually a mistake. I believe it's just .shp here. And there are some other limits in terms of the number of properties that you can have and the size of those properties. But if you can fit it into a shapefile and it's less than 10 gigs total, you should be able to upload that to Earth Engine. Yes?
If you had more data than that, do you bring multiple 2 gig shapefiles together and merge them into one table in Earth Engine?
Yeah, so the question is, if you have multiple shapefiles of around 2 gigs, can you upload different shapefiles and then merge them? I believe the answer is yes. Again, these become feature collections in your code, and you can call feature collection.merge on those. Okay, so that's just sort of the overview. And I have 3 case studies for you here. We're a little short on time, so it's not clear if I'm going to be able to get to all these. But the last one is the most fun, so I'm going to try to rush through the first couple in hopes that we can spend some time on the last one. And the first one is a frequently asked question that we get, which goes something like this. I want to export a time series because I'm going to analyze it in R, MATLAB, fill in the blanks of your favorite statistical or other software. And the answer is, okay, but we need more information to be able to help you with that. And the whole next part of this case study is that conversation that we have to determine how to best help you export your data. So here's the overall setup. We have a time series of imagery here. These are just Landsat surface reflectance scenes. We're going to filter bounds to a region of interest and filter date to 1 year, and then do some cloud masking in this mapped function here based on the fmask data inside those surface reflectance images. But the point that I'm making here is that the size of this collection is now 21 images, which is a reasonable number to work with and expect to export in a not too crazy size and format. So we have 21 images. And now we just load up the census blocks. So here's how that works. This is the ID of that public data set. And as I mentioned previously, that becomes a feature collection. So that text ID is fed directly to the feature collection constructor here. You could also import this. So if you're looking at the dataset description, you could click import and you'd have a variable very much like this sitting in your import section. The next thing that we're going to do is filter this to a spatial area, so just filter bounds on this table. And the point is that now we have a table of 409 features, which is also a reasonable number. So what I'm getting at here is that if you want to export a time series, so spectral values in each one of those regions from each image over time, you're looking at the cross product of 409 features and 21 images, which is a reasonably sized table. So how do you do that? Here's one way. You start with the image collection, which is referenced by the variable L8 here. Map a function over this image collection. And inside this function, first just select one band. And this is an important point because often people say, I want to export a time series of images in my regions. And if you have multiple bands, that is really confusing the issue. That's a third dimension to this table, and we don't know how to shape that thing unless you tell us how. So for simplicity, in this example, I'm using one band. And if you want to export the other bands, then you can certainly select the other bands and do another export. But for simplicity, we're just looking at one band here. And then we call reduce regions on it. And the collection that we want to use as input to the reducer is our subset of census blocks. And here I'm just selecting a single property, which is the ID of those blocks. But there might be other properties that you want as well. And we choose the mean reducer and, of course, the scale. Anytime there's a scale parameter, you should always set it. And in this case, we're using Landsat imagery, so the scale is 30. Next, filter this thing to make sure that the output of the reducer is not null. So if you have an image that's not overlapping one of your polygons, we want to eliminate those points. And map a function of the result to just set the image ID on each one of those reduced regions. So at the end of this, each region should have its block ID 10, so the ID of the region. It should have the output of the reducer, which is called mean, and it should have the ID of the image. So that's why we're calling this a triplet, because you've got those three identifiers, the image ID, the block ID, and the reducer output, which is the mean of the band 1 values inside each region. The result of doing reduce regions inside a map is a collection of collections. And when you have a collection of collections, what you need to do is flatten it to get out a single collection of triplets. So at the very end of all this, in order to get a single collection from a collection of collections, we call .flatten. Questions about this? Okay. This is what a single feature looks like that comes out of this process. It's, as I mentioned previously, a triplet. And what we have in this triplet is the ID of the census block, the ID of the image, and the mean, or the output of the reducer, which is the mean of band 1 pixels inside that region. At this point, you may be done. You could export this feature collection and open it in the software of your choice and do data summarization and so forth using just these triplets. And that might be the best option for you depending on where this table is going to end up and what you're going to do with it. But often what people want to do is in fact rearrange this thing into a table of rows and columns that you can then export in the shape that you want directly. So given that you want to keep going and reshape this thing inside Earth Engine, here is one way to do it. And apologies, I know this is a lot of code, but here's how I think you can do this. So first of all, this is a function. And we're just calling this function format, which means that we're going to shape this set of triplets in some way. And the first thing that we do is define the rows. And that's just the distinct values of the property that you want to be arranged in rows of the table. So we get the distinct values of all that, because there might be duplicates in this collection of triplets. So we just want the distinct values for the rows. And then we do a join. And what we're going to do here is essentially join the table to itself. And the primary collection is going to be this set of distinct rows or distinct row IDs. And the secondary collection is going to be the table itself. And the filter condition or the join condition is just that the row ID matches. So you want, for each row ID, the whole collection of triplets that has that row ID, which might have many different image IDs, say. So what comes out of that thing is a feature collection in which each feature stores a property called rows, and that property called rows, the property is called matches, and that property called matches stores a list of all the triplets with the same row ID. So first get that list, and then map a function over the list. And the first thing that we do in here is just cast the argument to the function to a feature so that we can have access to all the methods on feature. And then return a list which contains the column ID, which again might be the image ID, and it also contains the reducer output. What we're then going to return from this outermost map here is the row with the row ID, and here's the magic part here. We're taking, okay, there's some magic that I forgot about. The primary is the row, secondary is the table, there's the row ID, there's the row ID again. And now we're going to take this list and we are going to flatten this giant list of lists. And when you call flatten on a list of lists, what happens is you get a sequence of pairs. And when you give the sequence of pairs or the list of pairs to the dictionary constructor, it says, okay, this is a list of key value pairs. So I'm going to take the first thing, make it the key. The second thing is the value. Go to the next pair, and so forth. And create a giant dictionary in which the keys are the column IDs and the values are the reducer outputs. And that dictionary can be used to set a property on the feature. So you've probably seen this before where you say feature.set, and inside that, the argument to that set is a dictionary, curly brackets with a key value pair or one or more key value pairs in there. And so this is a quick way to take the row ID and set this dictionary of properties that corresponds to the column ID and the reducer output. So this is a lot of code to digest here, and I don't expect anyone to understand this, but this is the overall structure of it, and there's the link at the bottom. So you can adapt this and bend it to your will as necessary. But let me just give you a sense of what comes out the other end. First, there is the image ID. So if we specify the image ID as the row ID to that function that I just showed you, it's going to take the image IDs and it's going to arrange those in the rows of this table. Okay, the third argument here is the column ID. And we're saying that we want the column ID to be the census block ID, and here they are arranged in columns. There's also a table of geometries here, which you may or may not want to keep. But this is the structure of those triplets where images are rows and blocks are columns. So this is one of the ways that you might want to export this time series. So the regions are in columns, and the time series, if you will, are represented by image IDs and rows. So that's one way to get this thing out and into a format that you could then pump into R, MATLAB, or something else.
Can I ask you a quick question?
Yeah.
So I'm noticing that under the geo, they're all set to geodesic true. So is that when I bring in a shapefile, it's automatically setting the edge type to a geodesic?
So this was a table ingested by us, which is geodesic.
Okay, so it may not have been a shapefile to begin
This was probably not a shapefile to begin with. This is actually a Hector question, who's sitting right there. And the question is, when you ingest a shapefile, are the shapes automatically geodesic?
I work at a lower level than that.
I,
No, because it turns out that geodesic is almost never the answer you want.
we think the answer is no.
It's start thinking that, like, there might be an option in the future that, that the current situation, I believe, is that you get projected lines no matter what.
So this is easy enough to check. You can ingest a shapefile and print one of the features and look at the geometry, and if it's geodesic and you want it to be geodesic, then great, and if it's not, then you can map a function and change it to a non-geodesic shape. Okay, this is one of the formats you might want. Here's another format that you might want. In this case, I've just swapped the image ID for the block ID in the order of arguments to this function. And now the row ID is going to be the blocks, and the image ID is going to be the columns. And that's what you get. You get the block ID in rows, and this is, again, 400 or something. And you have a shape property, which you can keep if you want or not. And you have the image IDs in the columns, and then, of course, the reducer output in the body of the table. So this is just the transpose of the previous table. So the question is, do you want a table with 21 columns and 409 rows, or do you want a table with 21 rows and 409 columns? I don't know. But this is the way that you can get one or both of those formats and export this from Earth Engine. Questions about that example? Answers?
I just would add that be careful. Sometimes when you export, it's actually possible. I've seen it possible to have features that don't have. In this case, it wouldn't happen, but if you're concatenating feature collections together, if everything doesn't have the same properties, or if there's properties that are not filled, sometimes you can get rows that.
Yeah.
And then when you go to pull it into some other application, your CSV is hosed.
I actually had that example in here,
Oh, sorry.
but it's gone. And so the comment was, how do you set the schema of the output table before you output it? And this is probably a place where we could use some API sugar. But the example that I hate showing, which is why I took it out, is you make a null feature with all the properties that you want, and then merge it with the table that you want to export. And that forces the schema. So what we're talking about here is that if you have null values, and I think the previous example might have, yeah, okay, so here's a null example. If that happened to be the first record, you might end up with an output table missing this property for everything. And so what you can do is make an empty feature, set all the properties to some nonsense value, say, put that feature into a collection, call .merge on that collection, and that will force all the output to have all the properties that you want. But that is really a nasty workaround, and we need to fix that. But point taken, thank you. Okay, yeah.
What are have the limitations on exporting changed?
The limitations on exporting. Yes, they have been reduced. I mean, the limitations are reduced. Not the number of features. There are fewer limitations. And I'm going to give you a preview of that in a second. Okay. So much for the time series export example. Again, you guys now have all that code. And if you need to export time series for any reason, feel free to consult those examples and let me know if you have any difficulty. Okay. The next question is about the Global 200 ecoregions, which was this interesting paper by Olson and Dinnerstein, 2002. The 200 most important ecoregions in the world for various reasons. And there's this great paper that you can get to from this link, and you can also get a shapefile from that link. So the question is, which of these global 200 very important special ecoregions is most threatened by development or climate change or population change, for example? So let's investigate by overlaying these ecoregions on change images. The first thing is I go to this website and I download the shapefile. I click the New button from the Assets tab, and I select Shapefile Upload. I upload the shapefile. It ends up in my Users folder. If I click the dataset description, you can see this large blankness, which just includes the link to the website where I got this thing, and all the information you need is there. But if you have other important information, you can edit this description and say, oh, I downloaded it from that website and did some other stuff for posterity or for other users should you choose to share this thing. But I just downloaded and uploaded, and then I clicked the import button, and that put the data set into my imports, and now it's ready for use as a feature collection inside Earth Engine. And there it is. Again, I just fed the ID of this thing, the text ID, right into the feature collection constructor. You could also import this thing. At that point, you can add it to the map, and this should be like any other feature collection that you've used in Earth Engine before, and you'll have access to all the feature collection methods and so forth. So now images, I'm just going to zip through this because this is raster stuff, and we're not talking about raster stuff in here. I get two images of population, subtract one from the other, divide by a pixel area image in order to get population per area, or population change per area, convert the units, and that's it. So this is population change per area image. Nighttime lights change, so this is like a proxy for development, if you will. And I just get two images and subtract them. That's it. Land surface temperature change. Instead of having two images, I loaded the MODIS image collection, filtered it to two different 5-year periods, took the mean, subtracted one from the other. So land surface temperature increase or decrease. Again, this is just an example. I'm not claiming that any conservation decisions should be based on this analysis. You folks probably have a much better idea of the proper way to do this. But this was just sort of out of curiosity, where's land surface temperature changing. So subtract one from the other. Same thing with the Enhanced Vegetation Index, or the EVI. Load an image collection, filter it to two different 5-year periods, take the mean, subtract one from the other. EVI difference. Questions about any of this raster stuff? Okay, good. Let me check here. Okay. At this point, we can do everything at once. So, sorry.
The same thing you did with the LST, the land surface temperature, is it possible to do it with CO2 emissions?
CO2 emissions. Ooh, that is a good question. I don't know that we have CO2 emissions inside Earth Engine. Does anybody know? CO2 emissions? I don't think so either. That is a great question, and I wish we had that data set. Okay, so we take our change images, put them in a list, concatenate them into a single multi-banded image, and then call reduce regions on it with a mean reducer. So this is just getting the mean value inside each ecoregion of all those change images. So there's the collection. And at this point, let's say that you've done this, and you say, add to map of that giant reduction. So you've just done this, and you say reduce regions, and I want to add this table to the map and look at my ecoregions and investigate them, and computation timed out. How many people in here have had that error? Wow, okay. Let's say you have that error. Here's one thing that you will soon be able to do. So you folks can already do this, but it's going to go to a KML file in your drive, and then you got to turn it into a Fusion table. We are going to short circuit that process as well and make it such that you can click export on the feature collection, and it will go directly to an asset. And this will be ready in the very near future. I asked for a distinct timeline on that, but we cannot give you one other than very near future. You will be able to do this too.
And it will be announced on the dev list, right?
Yes, it will be announced, and you will all be able to profit from it soon enough. Yes?
And will it have similar limitations to the Shapefile side, less than 2 gigs?
The question is, are you limited by the shapefile spec when you export to an asset? And the answer is no. There's no shapefile in any part of this equation. And this thing will just become a table asset in your user directory.
But how big is too big for a table? Is there, I mean, there's a limit, right? How big should it be?
Hector, what's the limit?
At the lowest level, the limit is very high. I think tens of gigabytes. Well, for Google, that's probably not too high, but still tens of gigabytes.
Tens of gigabytes.
We have a few tables of
But in
a
terms of
couple of hundred gigabytes.
rows, number of rows is really what features.
Tens of millions?
Tens of millions, hundreds of millions, billions.
So
Trillions. If we're getting greedy, and that's what happens when you use Earth Engine, you invariably get greedy. That's what happens to me anyway.
So I think what we do internally is that you give us a table that let's say that is a terabyte, and we partition the table into small chunks. Not unlike imagery that is also partitioned into tiles. So when we partition the data in that way, a computation that is going to require to access a small portion of the table is still going to complete in a short amount of time, and there will be no problem, even if the full table was a few terabytes. And a computation that needs to go over the entire table, that's probably going to take a long time, but the system has been designed to be able to handle that. In that case, you probably need to run that computation in batch and then save the tiles somewhere. So I think this work brings the vector analysis a little bit more similar to the imagery analysis in Earth Engine. So the limits are going to depend more on what you're doing with it. If you want quick interactive response, you better be filtering the table significantly and getting a small subset of data. Otherwise, you probably need to run some batch processing.
So just to recap for the recording here, the question is, how big is too big? And the answer is it sort of depends on what you're trying to do. You can have many features, and if you're operating on a small subset on them interactively, it should be fine. If you're mapping a complex algorithm over the entire collection or the entire table, it's going to take longer, and you'll probably have to do that as an export, meaning in the batch execution mode.
Sorry to
Follow-up question.
I've been waiting for this day for.
Oh, we all have. And props to the engineering team who made it happen. Thank you very much.
The partitioning of the table, is it partitioned spatially? Is it organized? I think you alluded to this in the beginning when you were talking about how shapefiles and fusion tables are stored differently.
The question is, and let me just cut it short there in the interest of time, and Hector will be available afterwards. The question is it partitioned spatially? And the answer is yes, it is. And let me just move on because I really want to get to the last example, which is fun. Okay, so you've done some big computation with the table that you've uploaded or that you got from the public data catalog. You've exported it either to a fusion table, which you can do right now, or to an asset, which you'll be able to do soon. And once that thing is an asset sitting in your user folder, then you can just import it again and have the result. So just as a reminder of where we were, this is the table of ecoregions with the population, nighttime lights, EVI, and land surface temperature change as attributes or as properties. So now we've imported that table, and we want to look at it. And how do you do that? So the sort of the lightest weight method to visualize tables is called paint. And what you do is you take an empty image, and here I've cast it to byte, and be careful about that because it depends on the kind of data that you want to use. I've just cast it to byte here because I just want a population increase, and make a palette, and then paint this empty image with that table, and the color attribute or the color parameter that you specify in paint is going to be the property which will determine the pixel value in the output image. So each pixel under the ecoregions is going to have a pixel value according to the population property of the table, which I'll remind you is population change per unit area, or I'm sorry, per square kilometer. And at that point, you can just add it to the map. So this is an image, I add it to the map. Pop quiz, where does this maximum value come from? The answer is that I used the little visualization tool. So I go to an area of interest, I use the visualization tool to compute min and max, and then just hard-coded that value, so I don't have to do it every time. But you can determine that from statistics and so forth. And then specify the palette, which is going to be green to red approximately, and this is what it looks like. So areas of high-ish population change, foothills of the Himalayas in India and Nepal, and parts of Indonesia, and West Africa. So those are ecoregions that have had lots of population increase. Okay, another way to use paint is by specifying a width parameter. If you specify a width parameter, you get outlines. So in the previous example, I didn't specify width. If you don't specify width, it fills the polygons. If you specify width, it draws the outlines according to the width that you've specified here. So that's how you get outlines. Another way to do this is reduce to image. And so reduce to image is like an alternative to paint. This is another way to display a feature collection. And here what I've done is specified a list of the properties that we want to use. Call reduce to image, specifying that list of properties that we want. Specify a mean reducer and call dot for each on that reducer, such that we're going to get a mean reducer for each of the properties in the list. And as a result of doing that, we get a multi-banded image, which has a band for each of the properties that you've specified. So unlike paint, where you only get one band at a time, if you do reduce to image with a repeated reducer, you can have multiple bands. So now we have a single image with multiple bands, and we can display it. For example, here's nighttime light change per ecoregion. So developing countries, lots of increase in nighttime lights. Here is land surface temperature change per ecoregion. So northern places getting hotter. EVI change per ecoregion, and lots of other places having vegetation decrease. And the real question is, which of these ecoregions have this sort of combination of factors that might threaten the biodiversity within that ecoregion? So population increase, development as indicated by nighttime lights, impacts from climate change in terms of increase in land surface temperature or decrease in EVI. So how do we determine that? What I'm going to do is take the table and reduce columns on the table. This is how you compute statistics from tables. And the efficient way to do that is by specifying the reducers, plural, that you want by calling .combine on the reducers. And the result of calling .combine on the reducers is that you will have only one pass through the data, which is more efficient. So when you call .combine on reducers, you specify another reducer, and you should generally specify shared inputs to be true. And this will result in a single pass through the data. Unlike images, which automatically repeat the reducer per band, you need to tell the reducer to repeat itself. So in this case, we have 4 columns, or 4 properties, and so we call repeat with an argument of 4 to specify that we want this combined reducer to be repeated 4 times, once for each column that we want to reduce. What comes out of here is an object that contains 2 dictionaries, one dictionary for each of the reducers. So one dictionary stores keys of property names and values as the mean output. The other dictionary stores the properties as keys and the output of the standard deviation reducer as values. So we have 2 dictionaries and, we have 2 lists, and we turn those into 2 dictionaries using the properties as keys and the outputs of the reducer as values. Okay. Now this, again, apologies for the code. The complete example is there. And let me just sort of cut to the chase of this hoopla here, which is that we want to normalize each of the data in these 4 columns. And by normalize, I mean convert into z-scores by centering the data and dividing by the standard deviation. And so that's what we're doing here. We're mapping a function over the table, which first gets the properties as a dictionary. So when I call toDictionary on that feature, it's going to output a dictionary in which the keys are the property names and the values are the numbers that are being stored in those properties. Map a function over the dictionary When you map a function over the dictionary, that function takes two values, a key and a value. And so we just return the value with the mean subtracted. You just get the mean straight out of the mean dictionary. You get the SD straight out of the SD dictionary, divide by the SD, and return the feature with the normalized values, which is going to overwrite whatever values are there already. And that's it. This is just mapping a function over a feature collection in order to normalize the data using the stats that you've already computed. Now, finally, the punchline of this whole example is which ecoregions have experienced higher than average population increase, less than average vegetation change, greater than average land surface temperature increase, and greater than average nighttime lights increase. Again, this is just an example. There are undoubtedly better ways to do this, but I won't keep you in suspense any longer. Which ecoregions is it? Any guesses before I reveal the answer? Okay, so it's a good question, I guess. Forests, deserts. All right, are you ready? Drum roll, please. There they are. The 5 ecoregions that have experienced greater than average population increase, greater than average nighttime lights increase, less than average land surface temperature increase, and greater than average, no, I said that wrong. Greater than average land surface temperature increase and less than average vegetation change. And here they are, and so if you're doing work in these areas, maybe you can use this example to generate some more funding for your projects or something like that. Or feel free to tweak the example and make it actually useful for some conservation purpose. Questions about that before I go on to my final good, interesting example? Okay. The last one is a socioeconomic example, which is using census data. And here is the basic question that I was curious about. Does income correlate geographically with vegetation and or road density? And here is the way that I propose to answer this. I am going to start with census block group data joined to a table of socioeconomic factors, including aggregate income in each census block group. So start with this income table. Join by ID to this shapefile in the software of your choice. In this case, I used QGIS. The point that I'm making here is that this is a non-spatial join. And non-spatial joins are efficient in QGIS. So I did the non-spatial joining outside of Earth Engine, export the result to a shapefile, and import that shapefile to Earth Engine. And away we go. We have income data on all these shapes. Okay, so that's the income data. Next thing is that we want to look at roads data. And we already have roads. We have Tiger roads. And here is that table fed directly to the feature collection constructor. And here is the table that I imported. And all this stuff is shared with you guys. You know, all the code is there. You can go and look at the table. You can see where I got it. You can get your own tables and do the same thing and so forth. Here is the image collection that I want to use to compute vegetation attributes. And the first thing that we're going to do is join the roads to the census blocks, or the block groups, sorry. And the way this works is that first define a filter to give to the join. And the filter is going to be an intersects filter. And when you're doing a spatial join, you specify that the fields you're going to use are .geo. So by specifying .geo, you are performing a spatial join. And in general, it's good practice to specify an error margin. And that error margin is used in reprojections, if reprojections need to be done at some part of this process. We'll come back to this later, but if I don't care too much about spatial error, I will set this fairly high, for example, 10 meters. So this is in meters. If you are doing something with very high-res data or you really care about precision, you can decrease this to 1 meter or something like that, but things will get slower if you do that, so be careful. So spatial join with the geo fields. Oh, there they are. And what's next? We're going to save all. So the join here is from the roads to the block groups. And one thing that I want to highlight here is that these are both pre-filtered. So these have been pre-filtered to a non-crazy region of interest. And in general, it's good practice to only do these kinds of operations on the subset of data that you want to be in your analysis. Otherwise, Earth Engine will work hard to join everything to everything, and it might get slow, and that's probably not what you want. So it's good practice to always pre-filter the things that you're going to use in the join, or in any sort of overlay process, pre-filter everything. The join is a save all, so we're going to save all the roads that intersect each census block group in a property called roads. That's what this argument is for. So join, save all, apply it with the primary and secondary collections, and the condition is this intersects filter that I've defined up here. And finally, filter it out, post-filter the result of this join such that if there are any census block groups that didn't get joined to any roads, get rid of those. So we don't want any census block groups for which the roads list, this is going to be a list, is null. Questions about that? Okay. We are now going to compute road density per census block group. And again, apologies for the code, but let's just go through this bit by bit, and I think it should become clear at the end. So here's the joined collection. Recall that this is census block groups, each of which now stores a new property called roads, which is the list of all road segments that intersect that census block group. Map a function over this, so it's going to be a function of the block. Here's this list of roads. Recall this is the name that I gave it in the ee.join.saveall.apply function. So here's the name of the roads list. And what we're going to do is map a function over this roads list such that we're going to compute the intersection of the road with the block. Again, error margin of 10. And finally, take the length, again, error margin 10, that's what this argument is, take the length of that road segment that's intersecting the block. So all I did is I mapped a function over all the intersecting roads to essentially clip the road to the block boundary, and then compute its length. And finally, get the sum of all the road lengths. So the result of this is going to be stored in this road length variable. And again, this is the sum of all the road lengths intersecting that block. So total road length per block. Okay? And finally, set that road length just for fun. But what we really want is to divide by the block area in order to get road length per unit area. And here's how you do that. You just get the block geometry and call .area on it. Again, error margin. And then convert some units here. So that's how we get road density in each of these blocks. Questions about that? Yes?
What's the minimums of 10 and 1?
These are error margins. Yeah, and as I mentioned previously, this is probably could be a 10 in here as well. If you are, what's going to happen is that these error margins are used in the event that a reprojection needs to occur, and this is the allowable tolerance for changes in positioning that might result from that reprojection. And here we're dealing with big blocks and Landsat data, so I've specified pretty large error margins.
So like there's any like specific rule like less than half pixel or something? Have any idea for it? Like,
Yeah.
30 meter, right?
So the question is, what are those error margins doing in the arguments here? So here's an error margin, here's an error margin, here's another error margin. You should specify the error margin, and it should be and these are in meters, and it should be as large as you're willing to live with in the event that there's some error in reprojection. So my rule of thumb is I use 10 or 1. But you might have a better way to set that. In general, I'm pretty tolerant of errors, and so I just set it to 10. Okay, so now that we've done that join and mapped the function over the join to compute road density per area, we can now visualize the result. And again, I'm just going to paint an image with the result of road density per area and display it with a palette from white to red. And again, this max is determined interactively. And here's what it looks like for our little area. We are down in here somewhere. And so here is the Bay Area, and those are the census block groups with the greatest road density. Okay, so we have income, we have aggregate income per census block group, we have road density per census block group. The next thing that we want is NDVI per census block group. And here's how you can get that. First, just make a Landsat composite with the simple composite method. If you're in Knowles EE 101 condensed, you used this function pretty extensively, just getting a cloud-free composite for 2015. Compute normalized difference from that, and yes, I used the right variables here, so that's good. Renamed it NDVI. And then map a function over the blocks that have income and road length. And inside that mapped function, do a reduce region. So you could probably do a reduce regions here as well. Occasionally you might experience a timeout from reduce regions. So this is one way to avoid that, is to map a function with a reduce region singular inside it. There's a whole section of the docs about that in the debugging doc. So now we have mean NDVI, which I'm using as a proxy for vegetation in each one of these blocks. Questions about any of this? Okay, I see eyes starting to glaze over and emails getting checked. So I'm going to try to make things a little bit more interesting here. We're coming to the punchline. Here is the aggregate household income that we care about. Here is the roads per area and NDVI and that income property, just a list of the properties that we want. Here is a text description. And one thing that I've started to do here is to get a link, a code editor link. So you click the get link button, an encrypted URL comes into the address bar. You copy the encrypted part of that URL and burn it into your asset description and asset ID. The reason for doing this is then the name of every asset ID has this encrypted URL in it such that you can see the code that generated that asset. And this is sort of a fail-safe way to have that ability to replicate what you did. If you're like me, you don't remember stuff beyond, I don't know, a few weeks at a time. So next year I'll come to this data set and I'll say, what the heck? Where did that thing come from? Well, all you do is you take the name of the data set and paste it into the code editor, and then you'll know. So just a little habit that maybe it's a bad habit, I don't know, but that's something I've started doing. And again, export.table.toAsset. And this will go directly into my users folder. Coming soon. There it is. It's in my users folder. I import it. And the next part is about visualization, which maybe I'm going to skip in the interest of time. But pop quiz. Be the compiler. What is wrong with this code? Hint. I showed you the answer in an earlier slide. Hint. Reduce columns. Hint. Reducer. The answer is you need to repeat the reducer 3 times. This will fail. It'll say reducer expected 1 input and got 3 or something like that. You need to repeat the reducer. So here it is. I'm just reducing the columns is just to get visualization parameters for these data. And specifically, I want to know what the 5th and the 95th percentile are in each of these columns. So here's my display function. Reduce the columns, a percentile with 5 and 95, repeated 3 times, once for each property. And now I want to turn those stats into visualization parameters. Now, visualization parameters are an argument to a client-side function. So you can't use these server-side objects inside those client-side functions. So map.addLayer is a client-side thing. And if you give it a computed object for the visualization parameters, Earth Engine will not be happy about that and will let you know that you've done something wrong. So the solution is to call getInfo. And I can't believe I'm even putting this into a slide in a public presentation, but there it is. Watch out, because those getInfos will block until the stats have been computed, and then you can continue. But once you get those stats, you can just make 3 different images here using paint. So I'm going to paint roads into a variable called red. I'm going to paint NDVI into a variable called green, and I'm going to paint the income property into a variable called blue. You guys can probably see where I'm going with this now, right? The RGB image is just the red band, the green band, and the blue band combined here. Now I'm going to display it with these parameters for the 5th and 95th percentile for each of those bands. And the moment you've all been waiting for, what does that map look like? And here it is. This is my entry to the Earth Engine art contest, as well as the punchline of this case study. Again, red is road density, blue is aggregate income, and green is vegetation. And so you can see that some areas have lots of vegetation and not much else. Some areas have lots of money and not much else. Some areas have lots of roads and not much else. And some areas have combinations of the above. And if you are doing some kind of a socioeconomic analysis, this might mean something to you or be predictive of some area in the world. I don't know. But there it is. I call this the money map. Questions about any of that in our -0 time remaining? Answers about any of that?
How'd you make that legend with the color?
That legend is an image. If you search color wheel, you'll get images like that. And this is text placed onto the map. And you guys can see my cartography skills leave something to be desired here. But I'm the kind of person who can spend 8 hours or more making maps like this. So this is, the 1 hour version of that. Yes, we need legends in Earth Engine.
Are we looking at an image, a multi-band image, or a feature collection?
You're looking at an image. And here it is. It's paint 3 times from these variables. Paint is, the output of paint is then concatenated into a single image for red, green, and blue.
How would you know the resolution? How do you specify the resolution?
So the question is, how do you know the resolution of this? And the answer is, there is no resolution yet. That's not entirely true. The resolution is set by the zoom level in the code editor. So this image exists at whatever resolution you want. So if you were to export it, you would set the scale and tell it what you want the spatial resolution to be. In this case, it's just determined by the code editor. Yes?
Kind of related to that, I'm assuming that internally you must have simplified versions of these geometries. Is there an analogous, so when you do a reducer over, an image, you pick a scale to run that reducer at. Do vectors stored internally have any similar trade-offs in terms of precision? Do I have to specify that on stored assets?
So the question is, and Hector, please bail me out if I get in trouble here. The question is, do vectors have a resolution like images do? And the answer, again, correct me if I'm wrong, is no. The precision is specified when you do an operation such as an intersects, in which case you would specify an error margin. How correct is that?
That is correct.
That is correct. That's for the camera. That's why I'm repeating this stuff. Any other questions? Okay, I think we're done. Oh, We're not done. One more thing. Sorry. I'm out of time, right? I have minus 3 minutes remaining. Is that correct? Anybody? Yeah. Okay, so in my minus 3 minutes remaining, you might be wondering what is the actual correlation between aggregate income and road density, or aggregate income and mean NDVI, and here's how you find that out. Again, reduced columns on the table with a correlation, just a regular old Pearson's correlation here. And I want to know the correlation between NDVI and income and roads per area and income. And before I reveal the result, are there any guesses? How about sign? Positive or negative on these correlations? Yeah, vegetation and money, positive or negative correlation? Positive. How about, you say negative? How about the next one? Negative. Shall I reveal the result? Okay, positive correlation between vegetation, not a large correlation, between NDVI and aggregate income with a very small p-value, and negative but very, very small correlation on road density and aggregate income. Yeah, so this was for California only. And, but we have the entire US in our catalog, and wouldn't it be interesting to know? Any other questions? Okay, I guess I'm done. Thank you.